is B on the horizontal? A versus B. Okay, so is that right? You said B's on the horizontal?
Yes.
So so let's see, A goes from high values to lower values, B goes from higher values to lower values. Let me do that. Like this. Why would it be on a straight line? Well, A is going to be proportional to magnetic boost. Do you agree? Because force is equal to mass times acceleration, right? And the force is equal to, what is it? I, L, B, right? And also, this is true. The current times the resistance in the loop is equal to the magnetic field times the length times the velocity. So you take this and replace it, you get B squared, alpha squared, B. Okay, so A is proportional to the force. The force is proportional to D. So A is proportional to D. Right? Okay. So we've shown that relationship, and that relationship apparently holds up if you plot these data. Also, they gave you the length of the head, right? So if you took the slope of this, it's going to be, the slope will be equal to B squared L squared, right? Agreed? Okay, so you can find the slope of this, set it equal to B squared L squared. They gave you L, right? You know the length of the bar. So that way, the only unknown is B. You can solve for B. So you can figure out the magnetic field. That makes sense? So I think that's what they were getting at in part A. Part B, use your graph component to calculate the magnitude B, the magnetic field C, while the bar is moving which and both. Okay, that's just figure out the direction of the current's moving, and the side of the resistor that the current enters, that's going to be the high voltage side. That's going to be the highest potential side. Okay, so you can figure that out. Good. I think that's the whole thing. A wire with mass M are shown. A uniform magnetic field B is directed perpendicular to the plane and moving into the plane with the figure. The slide wire is given an initial speed of V0 when released. There is no friction between the slide wire and the loop. The resistance to the loop is negligible in comparison to the resistance part of the slide wire. A obtains an expression for the magnitude of the force exerted on the wire while it is moving at speed V. Show that the distance x that the wire moves toward coming to rest is x equal to V. NV0 R divided by L squared V squared. What is it? X is equal to M V0. What is it?
M V0 R over L squared V squared.
Okay, so this is how far it slides before it comes to a stop. Okay. Well, E over R. And that's also equal to B L E over R. Okay, so we take that, plug it in there, and we get B squared L squared B over R. Okay, so here's the relationship between the acceleration and the velocity. So the acceleration, which is equal to dv dt, is equal to b squared L squared over R times v. So that's the acceleration. So let's do dv over v equal to b squared L squared over mr times dt. Right? Now let's take the integral of both sides. We get the integral from b0 to b dv over v is equal to the integral of this with respect to time is just going to be b squared L squared t over n. Right? And you get the integral of both sides of this. Integral dt from 0 to t is just t. So this is natural log of v over v0 is equal to b squared L squared over mr all times t. Now we take the convert to exponent form, and we get b over v0 is equal to e to b squared L squared over r. I don't like that format because this implies that the I think what we want to do is no. For some reason I can I want a negative sign here. Okay, change the line separation. Because it should look like this. V is equal to v0, e to the negative v squared, L squared over r. That way it reduces to 0, right? So I've got a positive exponent here because this is positive because apparently I integrated wrong. Or, you know, they go. Okay, I know it should be this. Okay, because it's now reduced to 0. However, this is just going to go up toward infinity. Okay, so at time equals 0, the initial velocity here is v0. At time equals infinity, it drops toward 0. So it is correct here. But now, v is equal to dx dt. So we replace that with this, and then bring the dt over, and then integral dx, just x. That's going to be equal to v0 times the integral e to the negative v squared L squared over r t dt. Yeah. Now, when you integrate this, what do? You call all of this u, right? And then du. And u will be equal to negative v squared L squared over t du, which is that. So we've got a way of expressing dt, so this is n v0 V0 R divided by negative E squared L squared. Yeah, and integrating E to the U dU from 0 to T, put that in negative. Right. And so this is going to be M V0 R over negative E squared L squared. And if you evaluate this E to the U, which is negative E squared L squared T over M R minus 4. We've got a minus sign out here, which we probably don't want. So we can write this as x is equal to M V0 R divided by E squared S squared 1 minus E if you plug in time equals 0 here, 1 minus 1 is 0, so it starts out not getting traveled into. Okay, at time equals infinity, this basically goes away. So we've got all of this stuff. And what they say they wanted it to look like? Oh, that over there, M V0 R, E squared over L squared. Okay. That makes sense. Yeah. Well, what part of it did you not get? Oh, the negative sign.
Just like,
let's leave that underneath the carpet. A field to a toroid using Ampere's law, right? Okay, so you use that equation multiplied by A, the cross-sectional area of the toroid, okay? And that will be the flux, and remember L, the inductance, is equal to, what is it, capital N, E to D over I. Okay. And the hard thing, if you're figuring out the inductance of a new inductor, the hard thing usually is finding the magnetic flux. Okay. And we've already found the magnetic field due to a toroid. Just multiply that by the cross-sectional area of the toroid A, then multiply it by N, the total number of turns, divided by I, turn through it, then you've got the inductance of the toroid. And toroidal inductors are very common, and they're pretty easy to spot in a circuit because they don't make them small, okay? You know, they don't make them into integrated circuits, or there may be some toroidal inductors in integrated circuits, but in general, that's not necessary, and it's not dependent. Okay. Also, we found that the induced electromotive force across an inductor is directly proportional to the time rate of change of the current that's flowing through it. Okay. So the current flowing through the inductor is changing with time. The rate that it changes with time is proportional to the voltage across it. Okay? So this is voltage. This is the voltage across the inductor, this is the inductance, and this is how fast the current is changing with time. Okay? If it's changing very, very rapidly, then you'll have a very large voltage across your inductor. That's what that equation tells you. Now, do you remember the equation for power for an electrical device in terms of the current and the voltage? Right, I times D. So power equal to I times D, right? In this case, it's I times the voltage across the inductor. So the power dissipated by a changing current passing through an inductor is equal to the magnitude of it, L, I, E, I, right? We're only concerned with the power, not whether power, energy is being absorbed or released. So we're not concerned with the negatives. Now, power also is the rate that the magnetic energy is increasing or decreasing. Remember, there's a magnetic field, and so power, remember, is rate that energy is being used. Agreed? So the opposite side of that equation is L, I, the IG. So let's multiply both sides of that equation by the small increment of time required to make the change in the energy stored, the corresponding change in the current, and you get dU is equal to L, I, I. Now, if you integrate both sides, okay, let's integrate both sides of that, and we'll just have the total energy stored in the magnetic field enclosed by the inductor times, if you integrate I, E, and the I, what do you get? I squared over 2, right? So here's the energy stored in the magnetic field of an inductor. And remember, we did a similar thing when we figured out the energy stored in the capacitor, right? And then I mentioned that it was important not to just think in terms of the energy stored, but also the energy density, energy per unit volume. So we're going to do the same thing here. Remember, we use big U to represent potential energy stored in the field, little u to represent the energy stored per unit volume, right? So I'm going to do that. Okay, and that's going to be lowercase u. Okay, cross-sectional area times the length will give you the energy or the volume. And let's do this. Remember, what was, we found L for a solenoid last time, inductance. Did you help me out here? What was it? Capital N squared something? What was it? Capital N squared A. Yeah.
All over F.
Okay. So that was it. That's what we found the inductance to be for a solenoid. Let's take that and plug it in here and see what we get. So if we do that, we have n, capital N squared, A, U naught, okay, that's L, or a solenoid, times I squared. And we're dividing that by AL, but then we got an L here too, so we got an AL squared. Right? Now, N, capital N, is equal to lowercase n times L, isn't it? Remember, lowercase n is the turn density, number of turns per unit length, right? So the total number of turns over total length. Good? So let's take that way of expressing capital N, plug it in right there. And we do that, we'll have little n squared, L squared, A, U naught, I squared, all divided by A, L squared. So the AL squared goes away, and that leaves me with U to naught, n squared, I squared. And that's it, right? Now, if we square this, we have to multiply by another one on the bottom. But u sub 0 n I, that was the magnetic field of the solenoid, right? Squared. So we end up with that. So the energy density, the energy per unit volume stored inside that solenoid is just equal to the magnetic field squared divided by u sub 0. So, in other words, by the way, every aspect, any property that the inductor had is gone. All that's left is the magnetic field and u sub 0. Okay? So in other words, what this tells you is that energy is stored in a magnetic field. Wherever that, however that magnetic field is generated, wherever it is, there will be energy per unit volume in that region. Okay? How much? Well, it's related to the square of the magnetic field. If you double the magnetic field, you can quadruple the energy per unit volume being stored. And this equation is a whole lot bigger than this equation. Okay? This is the one that we derived for the energy stored in the electric field way back when we were talking about capacitors. And now we've derived a similar analogous equation for the energy stored in a magnetic field. Okay? There must be a similar equation for the energy density stored by gravitation.
I'm assuming you know the answer to that.
Well, I never assume that I know anything. I don't know everything. But I could probably derive it. What's that? Okay, so I got to here, right? And then I multiplied by 1, but I chose 1 to equal u sub 0 over u sub 0. So that squared that one and put 1 value. Why did I use to do that? Because u sub 0 and I is the magnetic field of the conductor. That's all. Yeah.
All of that energy volume or the energy density volume?
Big U is just energy, measured in joules. Little u is energy density, measured in joules per cubic meter. Yep.
What happens to the C?
2 in here. Where'd it go? Should be right here. Right here. Right here. And I guess this is supposed to have a 2 in it as well, does it? Does it? Yeah, no. One second, I didn't. I know that. I'm just rubbing it. Was my equation twice as good? Because I didn't do it.
You need to remember it.
Okay. Okay, so. Down magnetic field. LC surface. Okay. RL surface. We've done an RC surface. This is an RL surface. Okay. Notice that I misspelled it again. I think I got it right. And so a little squiggly thing is used to represent a resistor, and kind of a springy looking thing is used to represent an inductor. Okay. So you've got an inductor and a resistor in a circuit that's connected to a battery. If we close the circuit, if we close the switch that is, then the current can begin to flow from the battery through the resistor and then through the inductor. Right? And this is a battery, so a long time after the switch is closed, the current, or the voltage will be constant, so the current will be constant. At which time the voltage across the inductor will be 0. Because remember, the voltage across, let's just call it VL. The voltage across an inductor is proportional to L times di dt. So if we're driving this with a constant voltage, then that implies a constant current, and that implies di dt will be equal to 0. And so a long time after the switch is closed, this battery will be pushing constant current, and so there will be no voltage across the inductor. Remember, what is an inductor? It's just a coil of wire. Just wire. Okay? Voltage is not dropped across, just a wire. It emits a constant current. Okay? If the current is changing with time, then there will be a voltage drop across this inductor. Okay? And you can find it using this equation. So right after the switch is closed, at the instant the switch is closed, current begins to surge through the circuit. That's when di dt is the biggest. And that's when the voltage drop across the inductor will be the biggest, because it's directly related to how fast that current is changing. Does that make sense? Okay. So let's apply. Who's going? Yeah. Yeah, that's right. So we sum the voltages around this. Okay, going up, we have voltage across the voltage supply, then minus IR, then minus L di dt. Good. And then we're back to the start, and that's equal to 0. bring this term over, divide by L, and I'll have V S over L minus I minus R over L is equal to DI dt. Now I'm going to multiply both sides of that equation by dt. The small increment of time required to cause the current to change by a small increment di. And then I'm going to divide through by all this stuff on the left-hand side of the equation. If I do that, I'll have dt isolated. And on the right-hand side of the equation, I'll have di divided by ds over L minus I R over L. Yes? Okay. Now what am I going to do? Integrate. I'll integrate. Okay, to integrate both sides, if I do that, then this is just going to become t. There'll be t on that side, and on the other side I'll have the integral of pi over ds over L minus I R over. So all of this becomes my u, so du is going to be equal to negative R over L dt. Great. Only this part will remain after I take it rooted. Now, if I rewrite this, I'll have t is equal to the negative L over R integral du over u. Evaluate, what am I evaluating terms to? How about 0 to I? That's it. How about y 0? No. So minus L over R, natural log, and then let's convert back. And we'll have, what we're going to have on the top. Vs over L minus I R over L. On the bottom, we'll just have Vs over L. Okay, so it's going to be negative L over R. Natural log of, okay, this is just 1 minus I times R over Vs. Okay, now I'm going to multiply by R divided by negative L. I'll have negative R over L T is equal to the natural log. All that stuff, 1 minus R over Vs. Now I'm going to convert to exponent form. If I do that, I'll have e to the negative R over L T. That's going to be equal to 1 minus R over Vs I. Now bring this term over, multiply by Vs divided by R, and I'll have I isolated, I is 1 time, Vs over R, 1 minus e raised so negative R over L. And that should be the current. Let's see, at time equals 0. This will be, we'll have no current. At time equals 0. When you first close the switch, no current. What about at time equals something really big? At time equals infinity, e raised to the negative infinity is just 0. So it's just ds over r, which is just Ohm's law, right? So a long time after the switch is closed, then the voltage is constant, which makes sense because remember, this is just a coil of what? Wire. Right, okay. So it's just behaving like a piece of wire. A long time after that switch is closed, current flowing through it as if there's nothing there but a resistor. But at time equals 0, when you first close the switch, no current can flow. Why? Because the IDT is really big, and there's a back voltage at the inductor because you just closed the switch, so there's a big surge in the current. Right? So the IDT is big, the voltage across the inductor is big, so no current can flow from the battery at time equals 0. Make sense? Okay. Now, what is the voltage across the inductor?
After a long time, we're going to be this.
0. Should be. But remember the equation for the voltage across the inductor? What is the equation for the voltage across the inductor? Okay. So what do I have to do? I have to take that equation, take the time derivative of it, multiply by L, and I'll have the voltage equation across the inductor. Make sense? So, voltage across the inductor. And that's going to be, well, if you take the derivative of this, first term's gone, second term, what, negative is going to become positive, so R over L times V over R is V over L times L is just so there's the voltage across the inductor, negative Vs. So it counteracts the battery. Okay? Which makes sense. Remember, there's no current at time equals 0. At time equals 0, e raised to 0 is just 1. So at time equals 0, the voltage across the inductor is just negative the voltage of the battery. So it's like a mirror image of the battery and no current can flow. That's why I is equal to 0 at time equals 0. Make sense? Hey, at time equals 0, what would be the voltage across the resistor? 0. Why? No current. Voltage across a resistor is IR, Ohm's law. I is equal to 0, the voltage across a resistor is equal to 0. Make sense? So at time equals 0, when you first close that switch, all the voltage is dropped across the inductor. At time equals infinity, a long time after the switch is closed, all the voltage is dropped across the resistor. Good? Okay. Question? No. That's an RL circuit. An RL circuit. It can also be spelled LR. How do you spell RL? What's that?
I feel like the answer would be in the process. I know, right?